Our second review video covers questions 4 and 5. In question 4, we're asked to determine what the vertex form of the function represented by this graph might be, and or is rather. And so to do that, there's a couple of different approaches that we could take, I suppose, but this is the one that I like myself. You can use whatever works for you, and the key word there is works. Anything that gets you the right answer is okay, except for looking at the paper next to you. Anyway, we can see the vertex right here, and it's pretty clear that the coordinates are positive 5 for the x value and positive 7 for the y value. Well, we know that in the vertex form, this h is the opposite sign of the x value here, and the k keeps the same sign as this y value here. So we plug not positive 5 but negative 5 in here, and positive 7 here. Now our only unknown is a, the what will be the leading coefficient in the standard form. And so to determine a, we again look at the graph to see if there's a point that we can clearly identify on the graph, and it looks like this one right here, x is 10, y is 2, is it looks very much like those are the coordinates of this point that lies on the graph. And so we substitute 10 for x and 2 for y, or f of x. They are effectively the same thing. And solve for a. So 10 minus 5 is 5, and 5 squared is 25. So we have a times 25 plus 7. We subtract 7 from both sides of the equation, and that gives us a negative 5 on the left side, and a times 25 on the right side. We then divide both sides of the function by, or equation by 25, and so we have negative 5 over 25 is equal to a, and negative 5 over 25 reduces to negative 1/5. So our a is equal to negative 1/5. Now, to determine the standard form of the equation, we can just put the a into, we substitute the a into the form, the vertex form of the function, the incomplete form of the vertex, incomplete vertex form of the function that we came up with here, and then just multiply it out, expand, collect like terms, and then we will have our standard form. So negative 1/5 times x minus 5 squared plus 7. For that, I put square brackets around the x minus 5 squared, because that reminds me that I need to multiply all this out. I need to take care of these parentheses in this exponent before I multiply the negative 1/5. Excuse me. So x minus 5 squared means x minus 5 times x minus 5. And so we multiply our first terms. X times x is x squared. And our outside terms, x times negative 5 is negative 5x. And our inside terms, negative 5 times x is negative 5x. And then our last terms, negative 5 times a negative 5 is a positive 25. When we collect our like terms inside those brackets, we have x squared minus 10x plus 25. Then we distribute the negative 1/5 through all these terms. Negative 1/5 x squared is right here. Negative 1/5 times a negative 10 is going to be a positive, and it's negative 10 over negative 5, or 10 over 5, and 10 over 5 is 2, so we have positive 2x. and then negative 1/5 times 25 is going to be a negative, because it's a negative times a positive. 25 divided by 5 is 5, so we have negative 5 here. And then the last step is to combine the positive 7 on the outside here with the negative 5 here, which gives us a positive 2. So our two forms of the function are negative 1/5 times the quantity x minus 5 squared plus 7, and the standard form is negative 1/5 x squared plus 2x plus 2. So those are all the steps that you might want to take to determine those two forms. Now, I haven't gone through all those steps for the other three graphs. Those were just intended as extra practice. But if you go through the same steps that I just did, then you should come up with these results. For this graph, we see the vertex form is 1/4 times the quantity x plus 2 squared minus 4. And the standard form is 1/4 x squared plus x minus 3. For this graph, the second graph, the vertex form is negative 1/4 times the quantity x minus 2 squared plus 4. And then the standard form is negative 1/4 x squared plus x plus 3. And similarly for the last of these, the vertex form is 1/3 times the quantity x plus 3 squared minus 12, and the standard form is 1/3 x squared plus 2x minus 9. So if you practice these, you should get the same results that I do. All right, and now in number 5, we have a graph, and we're supposed to use this graph to determine the various values requested here. There aren't as many values requested on the actual exam, but this still makes good practice. Okay, so it says, how long is the rocket in the air? Well, this x-axis, the t-axis, is the amount of time that the rocket is in the air. Sorry, that point is extraneous right there. It's something that's in my program that I made this graphic with, and I forgot to take it out. But anyway, so 0 times 0, of course, is the time at which we fire the rocket, and these are the heights. The function gives us the height that the rocket reaches at any particular time, and we can see that it goes up, it comes down, and it reaches a height of 0 at 8 seconds, so the rocket's in the air 8 seconds. What's the greatest height it reaches? Well, that's the peak here, and that's approximately 256, as I recall it. That's exactly what it is, because this question is in your packet, and we did it in class. And the function is given too, so we can calculate this accurately. But on the exam, you'll only have a graph, and you'll just have to approximate these values. And so I say that the rocket height the rocket reaches, maximum height, is about 256 feet. About how high is it after 1 second? Well, after 1 second, we see that it's over 110, not as much as 120, and I'm approximating that to be 112 feet. At 2 seconds, how high is the rocket? Well, it's over 190, but not 200, and I'm approximating that to be 192 feet. At 6 seconds, how high is the rocket? Well, at 6 seconds, it looks like it's exactly as high as it was at 2, so that's 192 feet. Now, is the rocket traveling faster from 0 to 1 second, or from 3 seconds, here's 3 to 4? Well, it is traveling faster from 0 to 1 second. because in that time it appears to travel 112 feet, but in the interval 3 to 4 seconds, 3 to 4, the change in height is only 16. So farther in less time means faster. And finally, we're asked to write a reasonable domain and range for the event. The domain is from 0, x is 0, to x is 8. We indicate that in a number of ways. I got lazy and just wrote out 1 here. X is equal to 0, 8. The range appears to be y is equals 0 because that's where it starts. It starts at a height of 0 and reaches a maximum of 256 before it comes down. So the range is represented as y, or function values, equal 0 to 256. Now I used square brackets for each of these because the rocket does exist at both 0 and 8 seconds and at a height of 0 and 256 feet.